let's get started. So it's my pleasure to introduce the penultimate speaker for this season's seminar series, Dr. Mor Rozner, who is a member here, although she spent most of this year at the University of Cambridge, where she is a fellow at Gonville and Caius College and also a member of the Institute of Astronomy, but will be joining us full-time starting in September. Mor got a PhD from Technion in Israel, where she worked with Dr. Haggai Peretz, and she is interested in a wide variety of gravitational dynamics problems, from compact object mergers to star clusters to planetary systems. And she's currently on a quest to tell those of us who like to work on Platonic, idealized, conservative Hamiltonian systems that we really ought to worry about dissipation. So I think that's what she's going to tell us about today. So Mor, take it away.
Hey, thank you, Chris. Thanks for having me here today in general. And I will try to tell you about how gas reshapes dynamical evolution. And I will start from a short introduction. And I will tell you that no star is an island, and dynamics are affected by the environment. And actually, even not an island is an island, as you can see here. So because in an actual island, you can think about erosion, tides, and wind. All of them are actual physical processes that we actually model. So the dynamics is actually affected by the interactions with other objects, etc., and the environment. And stars, just like human beings, they have different lifestyles. So some stars prefer to live in distant or low-density villages. So those would be stars in the field. Some stars prefer dense cities. So those will be stars in dense clusters. And today we'll talk a bit about objects and dynamics in general in gas-rich environments, which are quite abundant. And gas-rich media are abundant over a large range of scales, starting from AGN disks or protoplanetary disks, which are the cradles of planet formation, star-forming regions, and gas-rich clusters. And all of them are interesting, and they share in common some parts of the dynamics. So what you see here, so supermassive black holes are abundant in general in many galaxies, and we even have one in our very own galaxy. So you can see here stars orbiting a point, and then people infer that there is a supermassive black hole there. We know today the masses, and people got the Nobel Prize for that in 2020. So those would be Andreas and Genzel. Okay. And around the supermassive black hole, we have star clusters. So those are the densest known clusters. They have something like 10 to the 6 to 10 to the 8 solar masses within a few parsecs. They're really, really dense. Just think about favorable dynamical implications. Since everything almost scales with density, the more dense you are, you will have higher rates of those effects, and we have a mix of all the young stellar populations in those clusters. So we have high density. So this is a fertile ground for interesting phenomena. I'll just briefly mention some of them, although all of you know better. Plenty of other ones. So we can think about tidal disruption events, or extreme menstruation spells, gravitational waves in general, all sorts of them, quasi-periodic eruptions, and many, many, many others. Okay, so how to form nuclear star cluster? So we have several models for that. So one of them will be globular clusters, and they migrate, merge, and that's that. Another option would be in situ formation via gas inflow into the cluster. And you have a weight migration scenario, which is kind of a mix between the first two. So that would be star formation during migration. And what you should take from this slide is actually gas is dominant in the formation mechanism of nuclear star clusters, which is good because we want to think about what happens in terms of dynamics in nuclear star clusters with gas. So those will be just some illustrations of what's going on in those formation mechanisms. So the upper panel will tell you about in situ scenarios. So you can see actually that you have some gas inflows. The second panel will be migration scenarios. So you see that you have some clusters and some gases clump, and they move through the clumps. And then you have the weight migration scenarios. So that would be the last one you can see there.
Good. Just to make sure I understand.
Yeah.
The numbers that you've itemized. So if I look for the example, in situ scenario, the number is 1 gas and flow 2. This is the time ordering of.
Yes.
Thank you.
Okay, so my point here is that nuclear star clusters can contain gas and quite, I would say, significant amounts of gas. So you can think about what will fuel this gas towards the nuclear star cluster. So you can think about gas inflows to the galactic center. Another smoking gun to having gas in nuclear star clusters is that we have a mix of old and young population. So that might tell you that you might have later star formation. Because if you have different distinct populations, you can imagine that you form one population, then after a while, you had gas from somewhere that help you to form second generation. And in order to form stars, since star formation is not that efficient, you have to have at least the amount of stars in gas, not more than that. So that tells you that you should have plenty of gas in those clusters. And we do have a deep gravitational potential, so that tells us that it's actually quite easier, I would say, to retain gas there. So then the question is, what should be the stellar distribution around the supermassive black hole? And this is a fundamental question that many people thought about how to answer. So I think the first one to do that was Peebles in 1972, and he derived the slope of n of r, the scalars r to the minus 9 over 4. So that will correlate with the constant particle flux. Then Bahcall-Wolf came and they suggested constant energy flux. So that would be, I would say, n scalars r to the minus 7, 4. And then we have plenty of generalization of that, but one of them will be Bahcall-Wolf for different masses. Okay, and I will show you a short.
Sorry, when you say flux, what does that mean exactly?
Okay, so that's a perfect fraction because that will be this slide. So I compare the Birkhoff level derivation of what's going on here. So we are trying to calculate what would be the typical number, distribution of stars in the cluster. So that would be NFR, and we say it would be power law, so that would be R to the P. And how will we do that? So we think about the steady state distribution. So we are interested in fluxes. So the particle fluxes, we define it, or if you want to think about that. So you have n stars, and each one of them is about to collide gamma in the rate of gamma. Well, gamma is simply n sigma p, so that would be gamma, and that tells you the rate of the collision with other stars. And then you want to make sure that this flux will be constant. So n is the number of stars, it scales as n, which is the number density times r cubed, and then you have n sigma v. You assume that sigma scales as 1 over v to the 4, v scales as 1 over square root of r, and then you put together all those powers and you end up with r to the power of 2p plus 9 over 2. And if you want to make sure that you have steady state, that means that the flux is constant, you actually have the Peebles distribution. So that would be constant particle flux. But if you want to think about the energy carried with those particles towards, that would be an outward flux, but it doesn't matter. So the energy carried with those particles, so you take the flux of particles, then you multiply that by the energy. So essentially what you do here is you just divide by r, because E scale is 1 over r. And with that, you are left with the Bahcall-Wolf distribution. Okay.
So sorry again. Constant means independent of r in this case.
Yeah.
Yeah. Can you elaborate a little bit?
So what I'm trying to derive here is a steady state in the sense that nothing goes out. Something goes out or in, but you have a steady state in terms of steady flux. So the flux is constant, doesn't change in terms of r. So that's essentially what I'm trying to do here. Only that. It's very simple.
So as many particles get heated as cooled.
In that sense, I would say, yes, although you do have flux. It's not a zero flux solution, right?
No, you still have a flux, but it's a steady state. So as many particles leave an energy bin as enter that energy bin. So that's a constant flux.
Mm-hmm. Yeah.
So if we have lots of young stars being formed and or things falling in, A, why should we expect a steady state in the first place? And B, if we do expect a steady state, what tells us whether it should be a constant particle flux, constant energy flux, zero flux?
So that's a tough question. I think one of my points here is to say that we don't expect steady state at all, because when you have gas, things will tend to fall towards the center. We won't have steady state. So, yeah.
How do you, suppose it was a steady state, how would you decide which of these is a good solution?
Well, it depends how you define good. So it depends which is the question that you are asking, right? I mean, if you think about energy, which is more natural, if you think about the phase space of the cluster, etc. So I would say the second one is more natural to use.
But it's, I mean, it's a basic observational question of, does the number density go like r to the -7/4 or 9/4?
Oh, yeah,
What would
okay, I
decide
get that,
what
yeah,
phase
then,
to decide?
I mean, if you think about observation, etc., I would go with the second one, although we don't have currently, I mean, observations.
I mean, idealized
Yeah.
observation is
Yeah, idealized.
atomic universe, yeah.
Yeah. And I'm
Why
going
the
with
second, why should it be energy flux? That's the main thing.
Um. Well, it depends, I guess, what would you like to conserve in the cluster, right? So, I mean, if you want to keep your energy flux constant, well, it sounds kind of iterative. So, yeah, maybe we should talk about that later.
Also, maybe it's unrelated, but these exponents, 9/4 and 7/4, if I'm not wrong, are exactly the same that one finds for like the adiabatic contraction of collision, that, like, for example, dark matter around something that grows adiabatically, like supermassive black hole. And you form exactly these density profiles with exactly these exponents. I don't know if it's related in any way.
I don't know where those came from.
It's an adiabatically growing
Yeah.
black hole.
So you start with some profile, then you grow a black hole at the center, and it will change the profile. And if you start flat, it becomes r to the -9/4. If you start with r to the -1, like NFW, becomes -7. I don't know if it's really.
Yeah, I don't know if it's an accident or, yeah, but I should take a look at this later.
Forgot Planck equation, that you're setting to 0.
So now we had gas, in order to perturb the steady state, because we have gas in cluster, so it's a short thing to do. And I will tell you a bit of introduction about gas dynamical friction. So, well, the dynamical friction would be, you have a very massive object, it travels in a sea of smaller objects, and then you have an accumulation of smaller objects behind you, so that's kind of a friction. And then if you replace those particles with gas particles, you'll have gas dynamical friction, which is almost the same, but with some corrections if you think about pressure, etc. Or you can just think about the dark. Those pictures, I mean, well, the left one is from Bruce, but the right one is definitely from here. And you can actually see the waves. Yeah, it was useful after all. Okay, so that will be the equation for gas dynamical friction. So the important things that you can take from here, it scales as well, the mass of the particle squared, the gas density that we are assuming to be power law with a power law gamma, and then there is I, which I'm hiding from you, but you can easily find in Ostrich 1999. And then there is the relative velocity squared. So that will be the relative velocity between you and the gas. Great. And there are some other models to treat motion in gas. So actually we don't really know what governs I would say the evolution of stars. In gas-rich environments, especially if you have a binary, especially if it is an eccentric binary, and it is under, active research. So people thought about several models. Some of them will be planet migration-like models. Other will be mini disks around each and every object that they merge or don't merge, or Bondy-Hoyle-like accretion-like profiles. Okay, so now we add an inward gas-driven energy flux. So the stellar flux, so the scattering induced flux is going outwards, and then we're adding another inward flux induced by the gas. So if we had a steady state beforehand, we won't have a steady state anymore, since some stars are going to the center. Okay, so that will be the ratio between energy fluxes. So what we did here was to go back and derive I would say, the diffusion coefficient, if you think about terms of gas. So the x-axis here will be the energy in units of E naught, where E naught is the energy at 0.1 parsec, and then you have the y-axis, which is the ratio between the fluxes. So F gas is the flux induced by gas, and F star is the flux induced by stars. And of course, as you increase the fraction of gas over stars, you have stronger and stronger effect, which makes sense. So typically in a cluster, it really depends when you ask this question, right? Because if you just form this expression right now, you should expect a higher fraction of gas, but that will decay. Some of that will get accreted, some of that will be expelled. But I think the most important thing is that even if you don't have order of one correction to the flux itself, you won't have steady state anymore, which is a strong thing to say, because it will still change everything in the cluster. Because you can think about the Bahcall-Wolf distribution with, I would say, a very weak perturbation that actually drive residual flux of stars towards the center. And then we studied a bit the parameter space. So here the x-axis will be gamma, which is the power law for gas, and the y-axis will be the fraction of gas over stars. The color stands for the flux of gas over stars in log scale, and then the green line tells you well the flux of stars is equal to the flux from gas. So you see, of course, the steeper the profile, the higher the effect will be. Well, you can see that by color, so that's that. Okay, and of course, if the power is shallower, the effect will be, I would say, weaker. And it changes with the mass of the gas again. So the higher the mass, the effect will be stronger. And here we thought about what would be the effect if we are thinking about the slope of the star. So alpha was the power law that we discussed earlier. So we have f to the e scalars e to the alpha. So if we change the slope, to remind you, alpha equals quarter will be the one which is related to Bahcall-Wolf cusp. And then we're thinking about if we are changing this alpha, what will happen in those terms again. So the y-axis is the gas fraction, the x-axis is alpha, and the color is the ratio between fluxes. And you see again, if you are steeper, you will have stronger effect.
So where do most clusters we observe?
Okay, so well, we don't know the constraint really well, how much mass we have in nuclear star clusters in general. If you observe clusters today, you won't have almost nothing. But if you think about the formation of nuclear star clusters, then you should have plenty of that. So I would say at earlier stages, it's fair to say you should expect something like between 10 to 30% of gas if you are just right after the formation of second generation, because you have to have all the mass of second generation stars like gas. So that gives you 10 to the 5 or like that. Okay. And that will be, I would say, a similar phase diagram, but now we think about different energies with the x-axis in log scale. Then the y-axis will be the gas fraction again. The color is the ratio between the gas and the star's flux, and the red line is again when it's equal to 1. And of course, when the energy, when you are closer to the center, you will experience higher effect. Okay. So why does it actually matter? So first of all, well, maybe not first of all, but it will give you an enhanced rate of many transients. So TDEs, gravitational wave, etc. So if you want to calculate the rate of those, you have to know very precisely what would be the distribution of stars. So if you change that, and if you change the flux of stars going to the center, that will change as well. It will be important also for rates of other processes in clusters, like binary critical formation, collisions, etc. It will change the rate of segregation and relaxation, etc. And we will feed this supermassive black hole on a different rate. And on the other direction, actually, it relates to Alex's question. If we don't know very well what is the gas density in clusters, we can set constraints on the gas densities from the observed rate of some other events.
These estimates are also assuming that the gas was spherically distributed in the same density profile as the stars.
So we checked several profiles. So, well, the stars are in certain profile and the gas profile is not necessarily followed them. So we checked, I think most of the plots I showed here stand for gamma equals -2. That's just
That's still spherical.
Yeah, still
You
spherical.
would expect the gas to be much more planar.
So that's a fair question. So we followed to begin with Bahcall-Wolf distribution, which relies heavily on having a spherical distribution. I mean, everything here is just in terms of energy. At all, we don't have angular momentum. So definitely one of the things that we're thinking about doing in the future is to think about this distribution, because it's more natural for other stuff as well. I mean, AGN disks, etc. It's very natural to think about them. That will be another extension of our model.
We can do these two limiting cases, one of the spherical distribution, one where you just collapse it all into a pancake. which would be more important for calculating, which would gas flux that you're calculating?
So I think it's not a trivial question that I would be very careful to answer that. I mean, the second one would definitely have higher densities of gas. So I tend to say you have stronger effect there.
Shorter time.
Exactly, but I'm not sure how will the angular momentum behave. It's not a trivial question. Yeah, we can talk about that later as well.
So how are you calculating this? Like, are you writing down the Boltzmann equation? And
So roughly speaking, what I'm doing here, roughly speaking, if I think about the fact of gas, I would say it's scaled with the number of stars I have, then how much energy I dissipate. Gas, so that's scaled as n times well, gas rod dot V. So roughly speaking, that's what I'm doing. And you can think about that as adding, I would say, a drift to a Fokker-Planck equation, but I didn't solve the Fokker-Planck equation for that.
and you equate that to the stellar relaxation.
So I just summed them up together. I mean, I showed some ratios, and then I mean the lines I showed here tells you what happens when I equate them. But I mean, it's not necessarily the case that they will be equal. Yeah. Okay. Then I move into the second, I would say, part, and I will tell you that binaries are abundant, and something like 50% of the sun-like stars reside in binaries, if not more, for higher mass binaries and higher mass stars. And we can think also about triple and higher hierarchies. They are abundant as well. So this rough plot is based on data from Duchenne and Krauss 2013. So the x-axis is the stellar mass and the y-axis is multiplicity, and you can see here that we have this fraction of multiplicity for all stars, especially for mass ones. Okay. So binaries are common over a wide range of scales, starting from planets or planet moon binaries. So one example of that would be Pluton-Charon. You can think about binary stars, binary black holes, and finally even binary galaxies. So everywhere you look, you see binaries. And a lot of interesting physical phenomena occur in binaries. So some of them will gravitational waves, or tides, or supernovae. If it's not enough for you, you can always add one object and it will be a triple and will become even more interesting. But no binary is an island as well. So the question is, what happens after an interaction with another star? So we have a binary, we encounter another star, what's going to happen? So that's a well-known question, and the answer would be, it depends if the binary is soft or hard dynamically. So what is soft or hard? So being hard means that the typical energy of the binary is larger than the typical energy of, in the cluster, and soft means that the energy of the binary is smaller than the typical energy of the cluster. And turns out that actually those two classes behave dynamically different when those binaries encounter some other stars. So Higgs-Hill's law tells us that soft binaries get softer. So it means that if you are soft and you collide another star, your separation will actually be larger, and being hard means that if you collide another star, then the separation will actually shrink. So you can think about that in a sense, just like you think about particles in the box, because it comes from the same, I would say, fundamental principles of equilibrium, but it's what happens for binaries. So if you're soft, you might get distracted by ionization or evaporation, because with each and every kick, you can get many small kicks, and with each and one of them, you will expand just a little bit, and then finally you will reach the tidal disruption. The tidal radius, and you will be disrupted. And you can have also ionization, meaning that you have one strong kick and then you are disrupted. And roughly speaking, you have one soft binary per cluster. I can maybe show the derivation, another derivation for that if I'll by the end. Okay, but the thing is that actually gas could save the day. So in gas, even soft binaries could get harder, because even if you are very soft, relative to the gas, you are still hard, because the gas will act to actually shrink the separation regardless of your initial separation. So that's good, because we want to save binaries later. So we actually want to define a new type of hard or soft binaries, but in gas-rich elements. So how we do that? So we have to sum up three contributions. So one of them would be stellar hardening, that will be the rate in which the binary will shrink the separation, and then there are softening, and the new thing that we're adding is gas hardening. So if you have a soft, meaning that the separation is larger than the typical soft hard binary, we just solve this equation. So we have two terms here. So you have the softening part, so that is positive, because the separation would like to expand, and then you have the gas dynamical friction. So usually everything here is positive, but now we are adding some negative part. So it could be positive, negative, or zero. And then if you're hard, meaning that your separation is smaller than the soft hard separation, we just have two negative parts. So you can only get harder. Okay, so those will be the equations for softening and hardening. So for the first one, well, you should take from all that, it scales with the, I would say, rho star, which is the density of perturbables. It scales with a square, where A is the separation of the binary, and over the mass of the binary, sigma is the velocity dispersion. And the hardening rate again scales with rho star and a square. That's that, and you already saw the gas friction equation.
So you're using Ostragon 99, which only works for straight orbits.
I do, yeah. So the answer is that, well, as I told you earlier, there are several models to model binaries gas. We are not really certain of what's going on there, but as long as you dissipate energy, everything will happen qualitatively the same for your favorite model. So it's pretty general in that sense. So that will be an example for soft binary that actually ends up being harder. So here the x-axis is the time linear and the y-axis is the separation in U. So you see that this binary is a soft binary. So if you just have softening without gas at all, you should follow the red line, and the separation will increase and increase, and eventually you will break. But if you add gas, actually this binary is about to end up harder. So the separation shrinks and you end up on a smaller separation. Okay. So we have also something strange going on. So previously we just had soft and hard binaries, but now we can have something in between as well. So again, the x-axis is the time in million years, the y-axis is separation. Then the black dashed line tells you what is the separation, the critical separation between soft and hard without gas at all. And you see, so the blue line will be an example for what we saw earlier. So we start soft, you end up hard. Then you have some strange binaries. So that will be, for example, the pink or the green one. So you start soft, so the separation still shrinks at the beginning because you are soft relative to the gas, but after a while, you don't have gas in the cluster anymore at all. So if you are not hard enough at this point, so roughly speaking, the time of the gas will be something like a few tens of million years. If you're not hard at this point, you will get softer eventually.
How do you take that into account, that gas is changing?
The gas density in my model changes exponentially. It gets exponentially with a typical time scale of a few tens of million years. And we can calculate a new soft hard limit, what we call the shielding radius. So the x-axis here will be the gas density in solar masses per parsec cube, and the y-axis will be the shielding radius. And as you see, it scales with the mass of the binary. And of course, the higher the gas density, the higher the shielding radius. So the shielding radius is the new limit between soft and hard binaries. So everything with radius below the shielding radius is considered hard relative to the gas. So we can gain some binaries, I would say, from heavy gas. Yeah.
What are some representative values of gas density that we find in different systems?
Okay, so, well, again, it's not observationally, we don't really find gas densities currently, but what I'm showing here, it's something like 10 to the 3 or 10 to the 4, so that's per parsec.
So then, for which system?
So that will be a cluster.
Early stage popular.
Yeah. But you can think about your favorite gas-rich environment, like everything there as well. So we have more hard binaries. So why is that important? For many things. So one of them will be having more common envelopes. I will talk a bit about that later, maybe. Gravitational waves, other transients, and more collisional dynamics, and also galaxy state binary formation. Okay. And now I will talk a bit about common envelope formation in gas-rich environments.
Mark, could you quickly go back a couple of slides, just one more? Yeah, so just so I'm getting the picture correct here, at the end stage in the blue curve, where it kind of is having this more catastrophic drop-off, is that transition where it's now hard and then and hardening without gas?
Once you reach this point, you are already hard, and you just have more and more encounters, and you are getting hard.
So we've got this kind of gas-assisted softening, gas-assisted hardening, gas dissipates, and then we're now in the hard regime, and then it can accelerate the other one. Okay.
Sort of gas densities are you thinking about?
So that will be something that 10 to the 3 or 10 to the 4, so once it's
So
about,
pretty,
Yeah.
pretty dense.
which is,
And those densities, are you thinking that is there star formation going on and
so if you
these
do.
stars secreting from the gas as
So,
well? And
yeah,
that-
so, okay, so that's a fair question. So people did see some different populations of stars and clusters. And then one of the, I would say, the leading explanations for that is that you had a later generation of star formation. I would say something like a few tens of million years after the first one. And if you do believe in this model, then you believe that you must have at least a mass of the stars, not in gas, to form them. And that gives you a decent fraction of gas in the cluster for a while. But after a while, of course, you will have some supernovae, they will expel the gas, and today, if you observe global clusters, you don't see the gas at all.
And for these curves as well, are you assuming a homogeneous density or some sort of profiles?
So those ones are homogeneous, yeah. Okay. So what are the conditions for common envelope formation? So the answer is we don't really know, but we do know what are some necessary conditions for that. So some of them will be that the donor has to expand beyond the threshold, initiate unstable mass transfer. We should be within a specific mass ratio, preference toward higher mass ratios, and we should have smaller separations, which should bring about, because that's exactly what I talked about earlier. And I told you this, I'm not sure what's going on there. Basically, small separation with this. And the whole population of binaries is about to get affected by gas. So if you look at this plot, so the x-axis is the separation in AU, or log scale, and the y-axis is the probability distribution function. And if you don't have gas at all, so you have only two regions. So one of them will be hard binaries, and then you have this region, soft binaries. But thanks to the gas, we have another intermediate region in which we have hard binaries that are hard relative to the gas, but not relative to the stars. So all the stars here are about to go left as well, which is good. We have more hard binaries, and then we have the soft binaries, which even gas can't save here. Okay, and you see that with time, actually, hard binaries get harder, they're going to the left, and soft binaries are softer, they're going to the right.
Are we in a nuclear cluster scenario here?
So that's a global cluster.
Seems like very broad initial distribution. They're really binaries at 10 to the 2, 10 to the 2.5 AU.
It's, if I remember correctly, it's a log normal distribution that I took, but I think I cut it for the very hard or very soft binaries. Because if you're very, very soft, if you're, even gas can't save you, and if you're very, very hard, I don't really care because you're already very, very hard. Yeah. Okay, and for even higher densities, even more binaries are about to get hard. So you can see it here. If you start from the dark blue and evolve after a while, that will be after 10 million years, for example, that will be the yellow line. And you see that you have plenty more of hard binaries. So the available parameter space of common envelope formation depends, I told you earlier, with the mass ratio, so that we Q the mass of the secondary of the primary and the same major axis. So in order to form a common envelope, it should be within some region, which depends also on the mass of the primary. So that's what we have here, and it comes from population synthesis plot. And what we are doing here is to combine those two effects. So we are asking ourselves, after a while, what would be the number or the fraction of common envelopes thanks to the gas? So that's what we are trying to do here. And on the left side, you have a population of binaries without gas at all. So we have an artificial cutoff here because we don't really care about hard binaries initially. And if you start from the blue curve, you see that after a while, if you don't have gas, you end up with having two populations. So those would be the soft binaries, and then you have the hard binaries. Yeah.
All right, you go, I don't know if it was one slide back or two slides back. Yeah, so the sharp cutoff below the red dashed line is an effect of the timescales.
Can you ask again?
So if I'm looking at this, going from dark blue to light blue to magenta to yellow, the fact that it's that like the PDF kind of stops at the red, that vertical dashed line, that's an effect of the timescales?
Okay, so I think what happens here, I mean, you have softening and hardening rates. So typically, if you don't have gas at all, you equate them exactly at this point and they will be equal.
Yeah.
So you will tend to stay here. So I think that's related to this point. So the left one we talked about, and the right one is what happens when you have gas. So if you start here from the blue distribution, as you start from the purple distribution and you end up with blue one, so you see that you have more hard binaries that you had earlier, which is good if you want to form more common envelopes. So common envelope to begin with relies heavily on the tail of the distribution. So even if we just have tiny slight increment, it's still really good for us because we will produce more common envelopes. So again, I'm comparing between the case without gas and with gas. So it will be the cumulative distribution function of what I showed you earlier. And you see the fractions of binaries being, to begin with, in this region of binaries that will produce common envelope and didn't produce common envelope in their initial condition is really tiny. But if you do add gas, we have a little bit more of them. So that would be an example. So common envelopes are indeed more common in gas-rich clusters. Well, they are common because you still have two objects inside an envelope, and they are common because they are abundant. And here the x-axis will be the time in million years, and the y-axis will be the fraction of common envelopes, meaning number of common envelopes over the number of stars in our sample. So if you don't have gas at all, we have a fraction of common envelopes. Some of them will die after a while because massive stars don't live for long. So that will be the dashed lines here. And if you add some gas, you have, say, a higher fraction of them. Again, some of them will die, but still it will be better than the case without gas. Okay, and another cool thing about closed binaries is that they can produce gravitational waves. So we have more closed binaries. You can think about production of gravitational waves in those regions. Okay, so we want to understand the evolution of compact objects now. So now we should adapt the contribution from gas dynamical friction, free body hardening that we talked about, and gravitational waves, because we're talking about compact objects. I will start from the circular orbit, and that will be just solving this equation for the semi-major axis evolution. So it is a complicated question to ask because now we're talking about binary dark, which is way much more complicated. You can see here that we have the interference between the wakes. Okay, and for larger separation, well, it turns out that actually we have a good separation of scales, although we just add up the contributions. And if your separation is really, really large, actually the thing that is dominated is gas dynamical friction, which we all know and we talked about. In the intermediate separations, we have free body hardening. We are talking about on hard binaries to begin with. So we have only hardening. So that is the gun from the first arc. And finally, if we are lucky, we will have gravitational waves. So that will be the famous Peter equation. Okay. So altogether now, so the x-axis will be the time in million years, the y-axis will be the separation they use, and the blue lines would be the critical separation to emit gravitational waves without anything else. So if you start from the purple line, red line, I'm not sure which color is that, but this one. So you see that gas is actually very efficient in the beginning, but after a while it reaches saturation because you don't have gas in the cluster anymore. It can't help you. But then luckily we have some free body hardening, and that helps you in this region. It becomes dominant here. And then eventually, if you add up also gravitational waves contribution and you think about everything together, you will get the yellow line. And then you will be able to merge within Hubble time. That's great. And gas hardening turns out to be really efficient. So thought about all the binaries between the softest to the hardest ones. So this would be the hardest one, this would be the softest one, and if you have high enough gas density, all of them would merge actually. And then you should ask yourself what happens in an eccentric evolution. So it turns out that gas dynamical friction is a bit strange. Because if you don't think about inclination, etc., at all, you don't think about disk, you think about all the spherical stuff. So with scale, the separation distribution scale is 1 over the velocity squared, and so does the force. So it actually means that the force is the strongest at apocenter rather than in pericenter. So it means that with time, we'll actually get more and more eccentric. So we calculated the orbit average equations, and then we thought what would happen if we think about eccentric binaries in gas. So roughly speaking, everything happens faster. So the upper panel will be the separation, or the pericenter in the U, the lower panel will be eccentricity, and you should compare the purple line, which tells you about circular binary, let's say to the one in red, which is typical eccentricity if you think about thermal distribution, and you see that the typical timescales are way much shorter.
Right, so it spends the most amount of time in the epicenter. And the force is also higher at the epicenter. That's why you make it more eccentric with it.
So any small eccentricity will be amplified in this model. There's no lower bound.
So yeah, well, under the simplistic model, yeah, but I mean, in reality, we are again not quite sure what I mean. How does binaries behave in gas? I think maybe Callum can answer a better question. I mean, better answer on how small eccentricity binaries will behave in gas rich environment. If you do use this equation, which might not be the right one, then yes, every small eccentricity.
And maybe I don't know if this makes sense, but I guess you're assuming that the density is the same at apocenter, recenter.
I mean,
Not
the scale of those binaries is way much smaller than typical scale of the cluster, right? So this assumption actually makes sense.
so maybe there's feedback on the.
There must be feedback, that is true. I mean, I'm not taking that into account here. But again, I mean, as long as you believe that there is energy and angular momentum dissipation, you will get qualitatively the same results. I mean, with maybe different rates, etc., but qualitatively the same. Okay, maybe we want us to
The qualitative in this paper by David O'Neill, more or less addressing this problem. There are different tracks through eccentricity same major axis space, depending on where you start. And I don't know that they all go in this direction.
Yeah, so, well, I should definitely test that with his models, but yeah.
There's some,
They do.
there's some corner that doesn't behave this way. But most of
It's a
it,
function of Mach number.
Yeah.
That's the plot, actually, isn't it? Eccentricity versus Mach numbers.
but qualitatively with this, I think the important thing is power, the torque versus power and the velocity. So this is, you describe the force, but also because the lever arm is bigger at epicenter as well, it'll sound way more of the angular momentum, thus pumping eccentricities.
I agree with that.
So it's even a bigger effect though.
Okay, so intermediate mass black holes and how to build them. So until now I told you how to harden binaries. I didn't tell you how to form them, but I told you the something about merge. So what happens if you merge one binary and then another one? So this one will produce a more massive black hole, and then the same for this one. And by that you can draw I would say very massive black holes, and maybe you will be able to form an intermediate mass black hole. So those creatures are something like 10 to the 2 to 10 to the 5 solar masses. And what we thought about will be what will happen if you just put an IMBH in the gas-rich cluster. So what we claim is that you might form a version of an AGN disk, but rescaled down. So that's what we call a midi-AGN disk. And we first checked what is the available parameter space. So the x-axis here is the mass of the IMBH in solar masses. The y-axis is in a U, and the red line tells you where there's a front-of-tumor parameter equals to 1, which is the critical radius if you want to form something stable. Then the color tells you what is this Q, and the different panels are different gas densities. So of course, the higher the gas densities, the smaller parameter space you have available, because it's harder to remain stable. But still, you have different radii. Even here, it couldn't be smaller than something like 10 to the 3 AU. What would be typical scales of those miniature disks? And then we use the rescaled version of Circuit-Goodman 2003 to think about what would a mini-AGN like this look like. So here the x-axis will be again the radius in AU, and the different panels are, this will be the gas density, central temperature, H over R, and kappa. And you see that, roughly speaking, it behaves almost like an AGN disk, just rescaled down. And for
Kappa is kappa is what?
kappa is the opacity here.
You say this looks like an AGN. I had no idea what an AGN disk looks like. How does this look like one?
I didn't bring something like that, but well, an AGN disk could be almost like the grid line. Roughly speaking.
Okay, but you've assumed that to start with, so what's the surprise there? You've taken a model based on AGN disks.
Yeah, it's not a
You've
surprise.
changed the units, and then you said, oh, it looks like an AGN.
Yeah, I agree. It's not a surprise, it's just a statement, yeah. I mean, well, I mean, nobody observes such an object, so we think, what would such an object look like? Okay, so one interesting thing that we might have is fast and spirals. So you should think about, well, the x-axis here in all those panels is time millinear, and then you have dispersion. Okay, so here we change the masses of the migrating objects, it scales with the mass, that's what happens. That will be the typical gas density profile, and it decays with time as we have less and less gas in the cluster. And then if you put the object in different separations, of course, the behavior will be different. And if you start from higher separations, it will take more time. And that will be what happens when you think about different masses of IMPHs.
We assume the wake of one to not affect the wake of the other.
Yes.
So and
I
that
mean,
is
here-
fine as long as they are further away, but once they in spiral get closer to each other, they are going to talk to each other.
Yeah, I agree with that. But here, I mean, it depends how you define a boundary, right? Because here, what you have is an IMBH and the star circulating at that, right? But yeah, I agree with that. When you're getting very, very close, definitely this approximation doesn't hold. And we can produce some unique transients. So if you thought about TDEs earlier, you can think about micro or centimeters in those environments, because you have a scaled down version.
Is this again some very short-lived feature, this disk?
It must be, yeah,
A few tens of millions of years.
I would say so, yeah. Because it's also very easy to destroy it, right? Because this won't hold for long. Okay, and you can produce also MRIs or IMRIs. Okay, I guess I don't have much time to this, right?
5-6 minutes.
Okay, so I think I will
7.
just briefly mention something and then I'll close. So all binaries in AGN disks are essentially triples in the sense that you have a supermassive black hole at the center. So all the binaries circulating, I mean, going in the disk are triples, triples with that supermassive black hole as the felt perturber. So what we thought about here is that those binaries actually goes in and out the disk, and once they do that, actually they interact with the gas in the disk. So that could modulate the evolution. And we thought about bit of quasi in gas-rich environments and what happens there. So essentially we have 3 regimes like everything in life. So if you have plenty of gas, you will completely quench the quasi oscillations. But quasi usually gives you some oscillations in extra inclination. If you have almost no gas at all, you just have quasi little mechanism with small corrections. And then I would say
You would quench in the case of lots of gas.
you might have some figures like that. Do you see that? No, it's not right. Anyway, okay, so I would say that you won't have at all. I mean, if your execution will be dumped very easily, then you won't have quasi.
There's an inner orbit and an outer orbit.
That's true. And both of them are about to
It's going
change.
to be brought into the plane of the disk, presumably.
So both of them are about to change, right? Because I mean, the binary itself crosses disks once in a while. And also the outer orbit, I mean, you have again the contribution of the gas. So both of them are about to change. I mean, with usual wind of course you don't change the orbit, the outer orbit at all. Now you do.
But actually, you can, well, maybe you're gonna get onto this, but often if you invoke something that does change the outer orbit, that increases the number of mergers because
Yeah.
you kick enough in the inclination until you get into the rocket.
Yeah, I agree with that completely. So that's, I would say, one of the goals of what we did here, to think about how will that change the number of mergers. Yeah, okay, so I would say the most interesting regime that we actually have is to have something in between, which I mean means that the contribution from gas and lid of quasi are essentially similar, and then you actually can't really treat usually the quasi approximation. And I think I will close by there. So I will move to the takeaways. So I think the most important one is that gas-rich environments are abundant and the dynamics in those environments are different. Also because you have enhancement of process, but also because you have some unique process that you won't have in gas-free environments. And you can couple the dynamics with dissipation in general and gas especially. So if you think about your favorite dynamical process, just a dissipation for it, I think become more interesting. Thank you.
A few questions anymore? And I asked about, you've shown us a lot of different estimates, places where this might be an important effect. Is there some tractable calculation that one can do properly? I don't know, simulated that you can do with and without gas, like what would be the first thing you go after?
So I think I would start from the simple thing. So the problem that we don't really know, even if we just have a binary and we put it in gas, we don't really know what will happen there. Alex can tell you. It could go, I mean, inward or outward. And I think there are many efforts of people for that, but we don't really know the answer. So maybe the responsible thing to do will be to get all those codes, set the very same initial conditions and see what happens and settle down on the model. So it starts from a binary gas. I mean, then accept the binary gas, find binary gas, and then I will move to an n-binary simulation.
So going back to some of your earlier stuff, when you were kind of putting in these toy models for how your gas density is changing as a function of time, and then that's giving you these various curves. And all that is just kind of like some prescription that you're putting in there. I think you're getting these interesting effects when your kind of stellar mass is comparable to your gas mass. And in that sense, you're kind of getting this distinguished regime. In which case the feedback on the gas from the interaction with the stars driving this flux of stars is also going to drive a flux of gas in some sort of sense.
I see.
Can you get some sort of sense of how important that feedback effect is going to be in terms of dissipating?
So roughly speaking, I think you can think about the mass of the star being comparable to the mass of the gas around you in order to make an important feedback. But I guess the more detailed calculation will require how many orbits will you move before you're doing something like that. Okay.
You know, sorry.
Should I think of young stellar clusters and smokier clouds as a good application of some of these results?
I would say so, yeah. I think those are actually the best charts that one can have, because I mean, if you look today in global clusters, you won't have any gas.
Is there any data coming from GNST that's gonna,
So I'm not quite sure about that. I should definitely check that.
just only because you need infrared to see stellar populations in the interior here, so I don't know if that's.
I'm not quite sure. I don't know.
The ozai with gas. Assuming the gas is confined to some thin disk.
Yeah.
And then there's an outer orbit and an inner orbit. And the gas interaction once per outer period is going to change both the energy and angular momentum of the outer orbit and of the inner.
Yeah.
So which is the dominant of those four things? Energy, angular momentum of orbit 1 and orbit 2, which is the dominant effect?
So I think angular momentum and outer orbit, but I should go back to my calculations to give you some exact number.
And is Okay. Yeah, I mean, then that does suggest that you can gradually change the relative inclination for yourself.
It of course depends on the gas density as well, right? Because if you don't have gas at all, then
Yeah. I mean, one way to boost the number of mergers, basically the way you boost mergers through this codec process is by changing the relative inclinations
Mhm.
by any
Yeah,
means
I-
necessary. Flybys, triaxial cluster, or whatever. So this could be another one.
Mhm.
Any final question? No, let's thank Mor one more time and sign up for dinner.